Hi, I'm Solal, and I'm going to present to you Safe Low-Level Code Without Overhead is Practical. This is both the title of the paper and the main takeaway I want you to get from this paper. First, let's define safety. When I say safety, I mean low-level safety. Don't crash and don't access memory you don't own. So crash freedom and memory safety. I don't mean high-level correctness, like make sure one tenant cannot access another tenant's data. This is an interesting property, but it's complex and well beyond the scope of this paper. Let's say you're writing a piece of low-level code like a network driver. If you write something like this in C, then maybe your n is below 0 or above the bounds of whatever chunk of memory A points to, and now you are writing to some memory that you don't own, and next thing you know, you have a heartbleed. Instead, you might want to use a high-level language which is safe, like Java, in which the compiler will insert checks. First, that your array is not null, because arrays can be null in Java, and second, that your index is within bounds. If that's not the case, then your code will throw an exception. It will fail in a controlled way. It will not simply crash in some undefined behavior or access a memory it shouldn't. But these checks have overhead. We could spend hours discussing how much overhead exactly that is and what is the acceptable overhead. We could discuss whether the branch predictor in the CPU mitigates some of it or all of it, but really fundamentally, the only overhead that everybody would accept is a guaranteed 0. How do we get there? Well, one option might be let's use heuristics. If we have a loop like this in Java, then the compiler can notice that n is always within bounds, and so it doesn't need to insert bound checks. But if you go to your favorite language bug database, then you will find plenty of bug reports that the compiler just doesn't elide bound checks in some specific case, even if it elides them in some other case that is very, very close, because the heuristic doesn't trigger for all kinds of reasons, like maybe some internal compiler optimization caused the AST to look different. Instead, the main idea in this paper is to use type invariants. So here is a piece of Rust code. In Rust, the type non-zero U32 is, as its name implies, a non-zero 32-bit unsigned integer. This means that if you want to use it to divide something, like 1 over n, then it is guaranteed that n is not 0, so you cannot be dividing by 0. So the compiler doesn't need to insert a check that n is not 0 because the type already states that. It's a very simple proof. The requirement of division is n shouldn't be 0. N has a type invariant that says it's not 0, done. So the main contribution of this paper is that we provide evidence that safe low-level code without overhead is practical using type invariants. Let's see some invariants. We'll do it the Goldilocks way. First, something that's too lax, then something that's too strict, and finally something that's just right. So first, an example of an invariant that's too lax is our example of Java array indexing. If you index A with n in this piece of code, well, all you know is that your A is some kind of array of integers and n is an integer. Okay, at least you know their types. This is not Python, but you know nothing else, so the compiler has to assume that A might be null or n might be out of bounds, so it has to insert checks. These invariants aren't strong enough. Here's an example of an invariant that's too strict. Rust works on the aliasing XOR mutability principle, which means that for any piece of data, either there are many read-only references, the aliasing case, or there is exactly one read-write reference, the mutability case. Rust's mascot is this adorable little crab, but this little crab actually hides a deep, dark secret. See, imagine that you're working with a network card. When the network card receives a packet, it will update its own state. In order to be able to tell that, well, there is this packet, the buffer is now in this place in memory, the counters for how many bytes the card has received have been updated, and so on. But this means the card has a mutable reference to itself. And in the Rust model, this means we are in the mutability case. So that means there is exactly one read-write reference and no other references. This means that even software should not be able to access this card. Because there is exactly one reference, it's the card referencing itself, nobody should be able to reference it. In practice, what this means is that If you would like to use a volatile read, which is necessary when writing low-level drivers because you want to make sure you actually read from the hardware, you have to use unsafe Rust. Deal directly with pointers, as the simulator says, because a volatile read does not make sense in safe Rust, because the type invariant is that, well, either we're in the aliasing case, there are only read-only references, so we don't need the read to be volatile because nobody can modify it, or we're in the mutability case, we are the only one who have a reference, so we don't need the read to be volatile because nobody else can do anything. This is an invariant that is too strict. Our crab actually turns into a little urchin, which is the actual mascot of unsafe Rust. And so in practice, this means that drivers written in Rust currently have to use unsafe Rust. Now here's something that's just right. Let's say that you could limit an integer type to some range, like between 0 and 9 inclusive, and then you could declare an array that is indexed by that range. Now, if you have an instance of this small type, you can index any instance of this small array type without any checks, because by construction, your index has to be in range. This is not a made-up example, this is actually the Ada programming language, which is quite old, but still has compilers currently being developed today. In this paper, we do a case study where we take an existing driver written in C as a baseline, and we translate it in C#, Rust, and Ada. For C# and Rust, we had to add extensions to the languages to add the kind of type invariants we need, but for Ada, we didn't need to add anything because it already has all of the invariants necessary. And in terms of performance, the safe drivers are as good as the baseline, but unlike our C baseline, they are proven safe. Of course, we hope our C baseline is safe, but we haven't proven that, whereas the compilers of C#, Rust, and Ada can prove that the drivers are safe, except of course for the language extensions for C# and Rust. Now, just because it's currently practical doesn't mean it's easy. Even for Ada, which has all of the type invariants we needed, it was quite hard to write this driver because the compiler is mainly designed with the goal of productivity and safety, not zero overhead performance. So it will still sometimes insert checks and you don't quite know why. If you have ever written a proof in a theorem prover like Coq or like very fast, you know that you have this interface where the prover will tell you, well, here's the thing I'm trying to prove, here's all the facts I have, here's the step where I'm stuck at. But a compiler doesn't give you any such information. A compiler just produces a binary, and then you have to go look at the binary, notice that there actually is a check that has been inserted, try to make a guess as to why it might be the case, change the code, compile it again, and hope that it worked. And if it didn't, change your code again. You have no idea why the compiler inserted the check. The compiler doesn't give you any information at all. In conclusion, decoupling safety from correctness is the key to enabling the automated proof of safety at compile time, which means there is no need for runtime checks that add overhead. Languages and compilers should target this. Language designers should add the right type invariants to their languages so that all operations that could be unsafe have a corresponding type invariance that can prove the operation trivially. Without any solver, without anything fancy, just the compiler can do a trivial proof. Compiler engineers should make sure their compilers expose enough information so that developers who want it can know why there is a check that's being inserted. Our code is open source. It has been artifact evaluated. Thank you.